Good afternoon, everyone. It is my pleasure to introduce our today's speaker, Professor Shankar. So maybe you are doing research in statistical mechanics already know him, Professor Das. But for all other students, just a brief introduction. Professor Das did his BSc and Master from Dept University and then Jawaharlal Science College. Then he did his PhD from Chicago University, and then he respectively done two postdoc, one at USA and then Netherlands. Then he was in several places for two times, probably in Bark, also sometimes in our institute also center and Shah Institute. And 1993 onward, he is in jail. So Professor Das is well known for his work in condensed matter theory, and he has more than 100 publications, and one of his he has a very good review of modern physics. So also he is also a member of all the three academies. Also he has the JC Bose fellowship. So today we will be talking on this title of today's talk is dynamic density functional theory for a Brownian fluid. So we have 1 hour, 10 minutes, then we'll take some questions.
Okay. Well, thanks for the introduction. Just one little correction. We never went to Presidency University. In those days, it was Presidency College. Okay, so the title of the talk is Dynamic Density Functional Theory. Density functional theory, of course, is a well-known term, so most people know it. One other thing I try to follow in this lecture is try to be as little technical as possible, but being a theorist, this is a talk dealing with equations and ideas, physical problems. So I don't have any simulation to sort of show on the screen, things like that. So it requires your attention when I follow the brief schedule. I sort of stop in the middle and try to summarize a little bit so that you get some idea of what I'm trying to say. Density functional theory is something people is generally familiar with. Now, generally, density functional theory in most cases is electronic density theory. What I'm going to talk about here is not electronic density. It's density functional theory as applied to classical fluids, which I work on. Classical fluids, gases, active matter, and all this. But so it's the statics or the equilibrium properties where it is mainly applied, but it has been applied also to study the dynamics. So that's why it is termed as dynamic density function for classical systems. And also the sense of the talk is not so much just density functional theory. Density functional theory is because you are talking or describing things in terms of a continuum field. So what I'm going to sort of more aim towards is to talk about generally field theoretic models that you deal with in condensed matter systems. You deal with the problem in terms of some continuum fields instead of when you have a bunch of particles which you are simulating or studying in a real experiment. You have discrete properties, and how or why we sort of describe them in terms of continuum fields. What are the advantages and what are the methods to deal with that? This work, part of the work, the main part of the work I'm going to discuss is done with Japanese physicist Akira Oshimori. Some work we started when I spent a year in sabbatical, not with him, but it just came out of some discussions. Now, in those days he was in Kyushu, now he's in Niigata, and right now we are working on some papers. are sort of touching. Part of the work also with Neil Gadot, he was my PhD student, he finished in 2018. So these are the main collaborators, but there are other things that I'll mention. So let me just go to the brief discussion of what sort of system. So you have passive systems where you have particles interacting to a two-body potential, the simplest sort of system. It can be data zones, it can be hard spheres. And they are generally Hamiltonian systems. Here I have given you some schematic sort of image of what sort of potential. It can have a repulsive part, it can have an attractive part, which is like this. And these two adds to give you a potential. It can be different kind of power laws. There is Hertzian potentials, all sorts of things. Then there are systems which are called more active systems. They are self-generating. That is, they have their own mechanisms of creating free energy. The self-propelled nature of those particles. So they are non-Hamiltonian. Generally, they are out of equilibrium. Now, symmetries and conservation laws play a key role in forming those sort of equations that I'm going to discuss. Suppose you have an isotropic system, then your variables are chosen accordingly, and then of course conservation laws of conservation. There can be other things also. Suppose you have a Brownian particle, which is much heavier than for its surroundings, so it has, by the very reason of inertia, its dynamics is slow. So you have in its dynamics the fast part and the slow part. So there are different underlying physical principles on the basis of which the equations I described are constructed. So that's one key thing that goes into this sort of model. Let me give some example. If I consider a system in which the dynamics is stochastic, the microscopic level. So what I mean by this, that whatever particles I am considering, their dynamics itself, of course, one can say it's always Newtonian, but it doesn't have to be Newtonian. Think of the particles, if these are colloid particles, then the colloid is surrounded by some fluid or some liquid or something. So for that, there are two kinds of motion. One is the motion of the big particle, which is heavy inertia, and then it is constantly hit by other particles, so you have a noise part. So the microscopic equation for the particle is, at that level, it is dissipating, and it has a noise, and it has some dissipating part proportional to the momentum, and then of course you have a typical conservative sort of term. If it is not a if it is not a conservative system or just a passive system, then this can you can write it as a force. But this is a general equation you can write for such a system. Uh, uh, and then you have a noise, which the noise is correlated to.
The point.
Okay. So you have the noise correlation, which is defined like this. So I have some relation between the dissipative property and the noise correlation. But remember, this is again just discussing. It's an imposed relation. It is assumed that it has something like this. If the system is surrounded by something in equilibrium, one can write an equation. But it doesn't have to be like that. One can have different terms driving the system in different ways. But generally, the structure of the equation is like this. These are calling Fokker-Planck. This has nothing to do with Fokker-Planck equation. But it's just called Fokker-Planck because you are dealing with both the position and the momentum. That's the only reason calling it Fokker-Planck. Don't confuse it with Fokker-Planck equation. So the microscopic dynamics of each particle is Langevin equation, which is sort of general term used for a dissipative this. And so this is a stochastic partial differential equation. One can actually simplify this and write what I call Smolotowski dynamics, which is again a term I use because I've reduced the variables by throwing away the momentum part. So I assume that the momentum kind of dissipates very fast, so this term is 0. So you can say this equal to 0, and thereby you get a simpler equation only involving the position variables or the configuration variables, and keeping in mind the Smolotowski, the contribution of Smolotowski, call it Smolotowski dynamics. So that's another type of dynamics. So the dynamics is simplified. The only microscopic variable in that case is the position variable. In this case, it's position and the momentum. And then, of course, there is the usual Newtonian dynamics, where the particles follow the Newtonian equation for motion. There, the dynamics is completely reversible as compared to the irreversible dynamics, and of course, it's deterministic, whereas this is stochastic. So there can be different microscopic dynamics like this. Then, in considering the dynamics of such systems, the general quantity that is looked upon in fluids or in matter or other systems is the conserved property. So the density, the momentum density, which are written like this. Now, remember that these are just definitions. Why it is defined like this? Because if I take this function, and this is not much of a function, it's a bunch of sum of bunch of delta functions, where these are microscopic quantities, goes from 1 to 10 to the power 23, and this is the momentum of the alpha particle. This is the mass of the alpha particle, which is assumed here to be same for all, which is an approximation for simplification. But you have equations of this form or definitions of this form, so that if you indicate this function, so-called function over a small volume, you will get the mass in that little volume, momentum of that little volume, and that's why they are called density and momentum. But one should keep in mind that this bunch of delta functions summed up. But one can show that if such properties are conserved, that is, if I take an integration of this quantity over a whole volume, that has to remain constant, then as you know, that there is some kind of balance equation has to be there. And so you have a current and this. So this is the standard form of to satisfy the microscopic balance equation. Now a lot can come on what J phi, this current is. And here lies the crucial approximations or steps in forming the theory of or the equations for such systems. So, for Newtonian system, you can construct those equations. It's quite simple, though painful, uh, in terms of those equations like density. And this is like a stress tensor, which comes out to be things like this. And it is the form of this kind of equations that one uses. Let's say if you have a bunch of particles, you want to calculate the stress tensor from the simulations, then you use these sort of formulas over some volume and integrate it and get stress tensors. You can calculate the energy current. They all fall into this sort of this kind of balance equations. What about the yes?
Fokker-Planck equation momentum was not conserved because the noise term, not conserved noise.
Yes. At the microscopic level.
Right.
At the microscopic level. You mean this? Yeah. So if I write it in this form, then it is not conserved. But if suppose this quantity is written with a gradient operator, so I have a gradient operator hidden in it, then it will. So it depends on what the friction coefficient is. then you can write this whole thing as your as a gradient. You can think of this being written as a gradient. If this have a gradient operator, then the whole thing can go into a gradient. So this is what we call conserved order parameter, non-conserved order parameter. Okay, so so this is the story with Newtonian dynamics. These are fairly looking simple, but then you can see this sort of thing. You can do different approximations, but there's not much you can do with them at the level of writing down continuum field theoretic equations. These are discrete things and involves really microscopic quantities. Yes, if you are calculating try to calculate a quantity from data, let's say simulations of 500, 10,000 or something like that, then you can use these sort of formulas to calculate it. But if you want to form equations for density not like this, but density being treated as a continuum field, then it's a different story. It's that sort of thing that I'll try to discuss. But let me first just indicate what is the case for stochastic dynamics. If the dynamics is stochastic, then you have an equation like this. I'm just taking the overdamped case, what I call the smaller dynamics. What one can show, and this is a very highly cited paper of 1990 by David Dean, that if it's a microscopic property, then you can apply the Ito's thumb rule for the evolution of this variable, and then you can show that so if this is the microscopic equation, remember this is just a reduced form of this equation. You have x alpha t, you can put it on this side and write h alpha in terms of u, and then you have a noise part which has some quantity. Now, if this has dependence on x, then this becomes a multiplicative noise problem. But if it is simple, then it is like this. You can put this equation in this form with certain identification of g alpha beta. But what Ito calculus says, and this also can be shown, that you can write any function y of this x, where what x is some function of y, doesn't have to be rho. In this sort of the derivative of y will be like this. Of course, if it is not stochastic variable, you can see this will be just this chain rule. Now, if I take y as rho, which was the density variable that I chose this thing, I introduced in the last transparency, then the time rate of change of y, and this is Dean's work, he showed that it satisfies an equation of this form, that del rho del t is is having a form like this. Now you can see this is now an equation in terms of only the density field, and it's an exact equation. There's no approximation in it. That given that you take this dynamics, it's an exact representation of the dynamics. In the sense, even if it was microscopically reversible Newtonian dynamics, you can write down Eulerian equations which are exact. It's something like this. So it is claimed as an exact equation, and the noise in the equation can be related to the microscopic noise to this sort of definition, and you get an equation of closed form in density with this, which involves the derivative of the U function, the energy, the interaction energy. If I assume it to be conservative system, if it is not, it will involve some product of the force times. Now, if this is the equation of force, then it is a closed equation in density, and this is quite important. Now, generally, what is done is rho is assumed to be some smooth function. It is simply just average density. But in principle, what you are obtaining is the microscopic density. I'll talk about this a little bit more in the next class. One thing I want to point out here, that keep in mind that if I do not introduce this sort of stochastic equation, just take the definition, I can still write a balance equation for rho, which is like this, which is the momentum density. And in this problem, there is no momentum density. Why? Because I have, through this over damping approximation, I've thrown away the momentum part of the problem. So now it is only a problem in the position variables, and so you do not have the g. But you can also formulate the equation involving g, which I call the Fokker-Planck dynamics, and then you will get similar equations like this, like Dean got, and this is what originally Akira Oshimori also got in his paper. This is in Journal of Physics A, I think. And so this is a microscopic equation equivalent to Dean's equation for the Fokker-Planck case. And these are the corresponding collective variables I've written here just for reference again. So these are the microscopic equations. This is the definitions, and then one can write down combination of these equations, which I have not complicated the transparencies with, for rho and g, similar to the Dean's equation. Now, let's just play a little bit with the Dean's equation. What one can do is, one can take that Dean equation, which is this equation, and reshape it, like you rewrite it with certain introductions. You can write it in a nonlinear diffusive form like this, where you have a Baire transfer coefficient related to the gamma naught, and then rho delta I del f del rho h. F is some kind of a functional, which has an ideal gas part, and this is called ideal gas part just to keep analogy with classical fluids ideal gas part. But all these are written in terms of the rho hat, which is the bunch of delta functions. And so these are not really, I would not really call them as functionals, but some definitions of functional in terms of this rho hats. And then similar relation follows. So you get a microscopic equations of fluctuating density. By fluctuating, I mean this rho hat. With the functional, this functional f, which has the Baire interaction, the u in it. U is the Baire interaction, because remember the force in the microscopic equation was derivative of u. So it's the two particle interaction in the system. So
now, this equation is also exactly he claimed or
which one?
this equation.
Yeah, I mean, this is nothing but this equation. I've just rewritten this earlier equation. This one I showed you. This equation, if you just rewrite this equation, you can put it in this form. Here I have written d naught. Unfortunately, I have written there db, but they are same. But other than that, this writing is just a rewriting of f. If you take this f, take a functional derivative, you do the functional derivative without bothering about delta function, of course. You can tell me that I can't take a derivative like that. Yes, that's true. But if I take formally the definition and then write it in this form, then I can write the equation in this sort of thing, what, as you know, we call a nonlinear diffusion equation. Why? Because here you can write it as a functional dB as a functional of rho, and then write it in the diffusive sort of form. That's why it's called nonlinear. And the ideal gas part is given by this, related to density function.
What of the noise part? It has got a rho is a half. Right?
Yeah, so that is a good question. So as you can see, if I take the microscopic equation, that has not this one, the Dean Kawasaki, yeah, this, right? So that doesn't have the rho. But when I take the equation for the collective variable, it brings with it an extra, because you can see in the microscopic noise there's a delta function coming with it. When you take the expectation value of this, you get an extra factor of density, and thereby the noise, although in the microscopic equation the noise was not multiplicative, now the noise becomes multiplicative. So in Dean's equation, the noise is multiplicative. Okay. So this is the key issue on this that we address, that density is just a sum of delta function here. So we need to take care of that. That we want to treat density in the way we treat it in a continuum field theory, hydrodynamics. That it's a function of space and time which has relatively smooth derivatives and all that. How do you get that? So this is where you force grain the equation. When did I start? I have what? How much time?
20 minutes.
I have taken 20 minutes, or I have 20 minutes.
You have taken only 20 minutes.
So I have another 30 minutes.
Capital.
Okay. So we need to force grain those equations. And for the Brownian dynamics, as I have tried, so this is like a reminding what I've said. Microscopic balance equation is Dean's equation. By force grading, you get an equation which I'll discuss, which is called the Dean-Kawasaki equation. We have Theory Kawasaki had a lot of equation in this sort of form. He worked a lot with this. So it goes by Dean-Kawasaki or Kawasaki-Dean equation. Then I'll try to touch how this sort of equation can also be obtained. This is for the normal Brownian motion. This is if you have active Brownian particles, then this can give rise also to the Kroner 2 equation. This is a work that I did with Sunil, and I'll try to touch on that. Another thing I'll try to mention that how those equations have breaking of Galilean invariance, because in those equations you have Galilean invariance, the microscopic equations in terms of momentum and density, hydrodynamic equations. But for self-propelled particles, this is doesn't maintain Galilean invariance. So when 202 introduced them, this was sort of introduced with some arbitrary factor being put. I try to justify it from a more microscopic approach. So that if I can go up to that, if the time permits. So what is macroscopic hydrodynamics? You write down equations like this. As you can see, there is simple density related to momentum. Density is a smooth function of x and t. G is a smooth function of x and t. These are sort of equations that you see in college level books. Simple hydrodynamics, maybe in school also they teach this. Is that you have rho as a function of xt, g as a function of xt, then your momentum equation like this. How do you get this? You just simply apply that that density is conserved, momentum is conserved. It does not require, and also this equation is something that I keep writing. But remember, this is this and this. If you use two, you can get the usual Navier-Stokes equation, which is written in terms of the current field, which is related to g by rho is equal to p. So the current equation is written like this, which is more the standard form of hydrodynamic Navier-Stokes equation. But these equations are obtained, keep in mind, even if you don't have a microscopic picture of a system. These are equations which are actually much more older than microscopic models. Even when people did not believe that matter consists of microscopic particles, these equations were dealt with because you can write down those as partial differential equations based on conservation properties, and you just define those fields, and then so whatever equation we write, it should conform to these kind of basic conservation laws equations. That's one thing. Sort of this gave rise, and this was first I think in Landauer's books and all that. What is called the fluctuating hydrodynamics. So the key point in this is that you have this microscopic quantity which depend on all the phase space coordinates. You average them over some non-equilibrium ensemble, and you get a smooth function of space and time. How is that guaranteed? Well, that's the definition of the smooth function. That if you average it over some non-equilibrium ensemble, it's supposed to give you a smooth function, and that's the equation. This is the fields for which we are trying to get, or we are trying to discuss the equations for. So these variables, they are a small set of variables based on conservation law or symmetry principles. Uh, they can give rise in broken symmetric systems goes from most that. Okay. Now the dynamics is now described in terms of the time evolutions of this continuum fields. So these are partial differential equations with noise, but those smooth functions and then calculation, correlation function, these sort of things can be calculated by averaging over the noise. This is one of the key reason, actually, underlying reason that such things are very useful, because if you write those fluctuating aerodynamic equations, you have a way to write down the correlation functions, the time evolution of the correlation functions, the nonlinear effects, and all that, which gives rise to theories like MCT and all that. So that's where the applicability lies. I'm not going to discuss the applicability, but I'll try to discuss how for the Dean equation you get the corresponding coarse grained equation. So first of all, you have noise at the microscopic level. Just to sum up again, and the microscopic balance equations are coarse grained to obtain the stochastic equations. uh, so this is what I'm trying to drive at. I just said this, but these are points to recall. First, you have the microscopic equations, then coarse grain it over a suitable ensemble to find out or construct field theoretic equations, which can be then treated with field theoretic techniques like Martin-Sergi-Arrows and all these kind of models, where you can average over the noise and calculate correlation functions. So that's why one of the key advantage of that's where lies one of the key advantage of doing this kind of thing. So when you coarse grain, I said you average over a non-equilibrium ensemble, and generally what is done simply you average over the local equilibrium. So you replace, I stress the word replace the non-equilibrium ensemble by a local equilibrium distribution. How do you define it? Suppose you have a completely equilibrium distribution. This is sort of how you will write, right? It gives an ensemble, beta A. So for each quantity, H, N, P. P is the total momentum, N is the not pressure. Here P is the total momentum. N is the number of particles, H is the classical Hamiltonian. So you get corresponding multiplying factor, beta mu, beta V. V is the velocity field, mu is the chemical potential, beta is the temperature. So these are thermodynamic properties. So this is what we learn in normal statistical mechanics course at MSc level. And so for a set of such variables, you get a corresponding set of thermodynamic variables. These are intrinsic variables, these are extrinsic variables, depending on the size of the system. And so this is a general form. A written in terms of integral of some field density, A. So it can be density, momentum density, number of energy density, and so on. So this is how it is written formally. This is what I sort of use exponential Ex, a set of thermodynamic fields times the local fields integrated over space, and you can define a corresponding probability distribution using a partition function like this. This becomes a partition function. Trace by trace, I don't mean quantum mechanics. I mean the sum over all the integral over all the variables and everything.
What is A hat?
Pardon?
What is A hat?
A hat is just a definition. Suppose I have A is any one of these, right? So I can write A as an integral over a corresponding microscopic field. So you have rho hat dx, that will give you the number of particles. You have g hat dx, then that will give you the corresponding momentum, and so on.
X in and X. What is the difference?
This
X and X in. First thing.
this I mean the whole set of things. I mean your x is coordinate of one particle, x1, x2, x3. So that is of all the particles. When I say x here,
Oh, achha,
this
this is field value.
yeah,
Right.
this is a field variable. This is just a label. Whereas this means you are considering the set of x1, x2, x3 up to 10 to the power 20.
X is position.
Huh?
X is position.
Position. That's right. And then gamma means the whole set of it. If you have more variable p, this that. Okay. So one of the things that is done to deal with this sort of thing is consider the fluid I bought it. Whenever I try to use it, either in battery does or I forget it or something. Okay, so the equations are constructed by using a general trick that you consider the fluid from a locally moving frame and from the lab frame. To go into a locally moving frame or transformed equation, then you can write this in the prime frame. The idea of this was used by the Russian scientist that you can consider the fluids uh, from a locally rest frame. That means there the system really looks like an equilibrium. You can apply all the equilibrium formulas. So one can look at the equations from this sort of frames, and then if you make this transformation from the microscopic variable, they are related in the two frames in this sort of way. So if you average the momentum variable in this thing, then naturally you will average this, and this will become zero because the system is symmetric in P alpha prime, in the local rest frame, and so this will drop off, and you will get G as the current times the density, and so. So if you want to learn more about this, I'll say that you look at the paper. But using this sort of transformation of that, you can write. Now you can see. So I have averaged the rho over the microscopic ensemble of the local equilibrium ensemble, and that's why I have dropped the hats over the rho, not just for any sort of choice of symbol. It is dropped because the rho hat has been averaged. So if I take the Dean's equation, average it over the local equilibrium system, then you get an equation of this form where you have a product of two fields. This is where things can be very different because you have to calculate it. So to calculate it, you introduce an operator like this. This is called L, but remember it doesn't have to be Liouville operator because this may not be Hamiltonian operator. So this may not be del H del P alpha. I can just write it as P alpha, define it, and then write this as the force. Then it will be a different sort of order. But just to keep in mind Hamiltonian system, we have used the symbol L. But the main point is when the L acts on rho, it gives me the rho, the del dot A. This is exact. And I can act it on G, and this is a little bit algebraic. Maybe it is not business to discuss all this kind of details. If you are interested, then I can suggest look at the paper. This is typically viewed in 2013 actually, which movie. So basically, this 2-point function you can replace in terms of this kind of momentum correlation, momentum density correlation. The only assumption you want to make is that the momentum density correlation has reached some kind of an equilibrium or whatever you call that, that it has reached some kind of temperature or thermalization. If you don't want to call it temperature, then one can say that the average velocity has reached some value. But if we use this sort of thing to define an equivalent temperature or average velocity of the particles, then this whole thing reduces to this sort of form: rho x delta I mu x, where mu x is the chemical potential of the system. Where the mu x enters to this. So if I now just use this and use it in the Dean-Kawasaki equations average form, I can write that equation in a much more simplified form. I just need to also indicate that the density functional theory, F is written like this, the free energy, Helmholtz free energy, and the chemical potential function is written as a derivative of F. So that is how I will replace the mu in the Dean equation, average Dean equation or Dean-Kawasaki equation. The noise part can also be written in a similar way, but the noise again has to be averaged over the local equilibrium ensemble, some Barth variables. So it gives rise to this sort of average density in the system. That is, you interchange the averaging process, the local equilibrium and the Barth variables, then write this as an averaged density variable. So this is where the multiplicative nature comes, that it becomes a function of the average density. And so one can finally write this equation in this form. Remember, this was the origin. I just written it for reference. This was the original equation, the exact representation of the microscopic dynamics, which I talked about earlier, where everything is hatted and F is given by this. When I average this over the local equilibrium ensemble, I can write it in this form, where F is the free energy, but not a functional like this. It's the free energy that we use in the density functional theory. So F has two parts now, as usual: the ideal gas part, excess part, and then ideal gas part. And none of these are hashed. These are all related to the smooth density variable that one would generally use in a classical density function. So now these different derivatives of f are the direct correlation functions, which you use in the liquid state theory or everywhere. The 2-point part is the famous Einstein-Zernicke formula. So, so you uh, what you get is starting from the microscopic equations by averaging over the local equilibrium ensemble, you can get the usual equation for the density variable. But it is the density variable, as I said, with the driving part, which is dissipating part, and then you have a noise part. So this is what you can call an equation of fluctuating hydrodynamics also, which involves only density variable.
Psi also must be a gradient type, right?
This
Noise. Punjab noise.
not in this case. I mean, I can choose. The main point is that the xi, if a xi is not theta, I should put a theta hat here. But the xi correlation has the density variable, the local density. That's why it's a multiplication.
Yeah, no, but the original Bean's equation, it was a grad of a noise. I mean,
No, it's not there.
no, grad of rho factor rho half.
So this is this. Capital. By xi, you mean this,
Yeah,
this quantity,
grad
right?
of something.
This doesn't have to have a derivative. You can define a derivative.
Otherwise, conservation of
Just this one. This equation, right? So you have this, and this is the original xi. So you can write xi. Okay, you're right. This is derivative. You're talking about this derivative, right? Yeah, because it has to be other. There's a derivative in front of it, so it will be there. Okay. Same thing happens with Fokker-Planck equation. I have only told you in more details about the Dean Kawasaki equation, but you can do the same thing with both momentum and mass density and momentum. Remember the Dean Kawasaki was only an equation for rho. Now you write two equations and get similar equations that are used in fluctuating hydrodynamics. And here are some of the ways to get it. And then when you obtain the force-gain equation, they have the full structure like this. You have del Gi del T, the Navier-Stokes term, and all the terms show up when you average over the microscopic equations, the exact balance equations, but not the Dean equation, but the I would say the Dean Oshimori equation, where you consider both position and momentum. So these things all work out nicely, and if you are interested, please see the paper. Here, I want to also indicate one thing. So far, I have only talked about Brownian dynamics. What if the particles have microscopic dynamics, which is Newtonian? So in that case, fluctuating hydrodynamic equations have also been written, and they are generally of this sort of form. Here, if you start from this equation for Newtonian dynamics, remember for Newtonian dynamics, this can be obtained by introducing certain approximations because you do not have dissipative terms in Newtonian dynamics. So you introduce them phenomenologically, and then these are sort of like TDGL forms of equations. So for Newtonian equations, Newtonian system, you write similar equations. Then what Kawasaki showed actually that if you assume Kawasaki and also from Japan that if you apply the adiabatic approximation or the overdamping approximation at the level of the fields, you say this equal to 0, then you can write the combination of these two equations in a form like this, which is very similar to the Dean equation, and that's why actually Kawasaki comes in this Dean Kawasaki. That you write this equation in this kind of form, which is very similar. Then you know, which you write in this kind of, again, nonlinear diffusion equation that we were talking about for Dean Kawasaki. So to get from for the Newtonian system, you need this adiabatic approximation or overdamping approximation. You need that anyway also in the microscopic level in the Brownian dynamics by going from Fokker-Planck to Brownian dynamics by doing this overdamping approximation. So in every case, the continuum equation looks sort of similar if it is only for the density field. And this is the structure, and this is what is called the Dean equation or Dean-Kawasaki equation generally in the literature. These can also be put in a form like this, that this is what we call the general TDGL form, that you can write the time you have. So suppose you have a set of fields which are called phi A. So we can consider a case with only the density or density and momentum. You can write them in a general form like this. Then if you just take the density as one variable, then you can see naturally there will be no current term because it will be involving this Q, which is the Poisson bracket between the variables. So if you have the only one field, the Poisson bracket between the same field is 0. So the dissipative part is the reversible part is not there. You will get an equation only involving this term, and this is like the Dean-Kawasaki. So if you think of LIJ as a thing with a double derivative operator form, then it takes this sort of form, which I has to be identified with
So, Shankar, just one minute. Structurally, this equation del rho del t.
Yeah.
This looks like essentially modified Fick's law, right? Where it's a divergence of the rho of f.
Yeah, you can
like
call
a dynamic force.
You can call that. But there is some kind of effective force.
Yeah.
And it's something like that. Well, you see, these equations are like that. They conform to the more well-known form. But what I'm trying to show here that they follow from really microscopic dynamics. That's the essence of all this.
So, D naught is still the bare definition.
Yes. D naught is related to that microscopic
Single
equation.
particle.
Single particle. So when you write it in this form, you are asking about this element, right?
Yeah.
So this is a general form. If you look in the early book papers of Halperin and these people, dynamic critical phenomena, when they consider the dynamics of a system in terms of fields, in critical phenomena, study of critical phenomena, continuum theory, the dynamics of the field is written in terms of a reversible dynamics plus a dissipative dynamics and then a noise. So this involves Markovian approximation. It can apply for magnets. It can apply for fluids. You can consider this sort of equation only for density and momentum both for fluids. For magnets, you can consider this the order parameter. So this is like an order parameter. You can consider it non-conserved order parameter. You can consider this kind of equations for crystals. For liquid crystals, lots of work are done. With this very nice paper by Martin Perdikerson, which started with that. Then huge lot of work, serum. In active matter, this kind of equation is systemically used. So this is a general form. So what I'm trying to say is that if you take only the density, then it takes this sort of form. If you take a description with all density and momentum, which I have so far described to you, it takes this sort of form. We have two equations. First equation, intrinsically reversible only. It doesn't have any dissipative part. And then you have the momentum equation. So this is the fluctuating hydrodynamic equation. It is this equation from which mode coupling theories on this can be obtained for glass.
These are connected to transport coefficients.
It is transferable. And here the L naught is written in a scale form to mu naught. And this is the pressure term. This gives rise to delta IP. This is the term which is the Navier-Stokes nonlinearity or the Galilean invariance term and so on. So when you consider A and B, you can see the free energy in the two cases are different. One is what I call FU rho and another is what I call F rho G, because here it's a function of two variables, here it's a function of only one field. Here it's a function of two fields. Now what turns out from all this is that you can write these two related to this. The dissipate the kinetic part is written in this form. I cannot go into all this, but it is this form, whereas the rho is in the denominator, has a lot of very interesting physical consequences in classes and all other things. It is this 1 over rho that shows up in the 1 over rho here also. So the functional form is like this. Now, these sort of thing can be actually generally obtained also from this. Let me skip this part. Yeah. So if you take the free energies in this sort of form, log average of the log of the local equilibrium distribution function, you can obtain the free energy. What we could show that you can get the similar relation from this sort of analysis of the local equilibrium distribution function. You can take the local equilibrium distribution function like this, and then take the log, and then calculate this for the chemical, the F as a functional of mu and V, and then do a Legendre transformation to go to F as a function of rho and G. When you do all that, and you do it for the case with rho and G, and also for the case with rho only, you see this sort of relation that comes. So the free energy functional in the two descriptions of the field theory, one with rho and G, another with only rho, are related in this way. But keep in mind that this description also involves this adiabatic approximation or overdamping approximation, whereas this does not. So there is an underlying assumption from going to the rho and G description to the rho description. If I just take the f of rho G and functionally integrate out G, I would not get the f rho, because if you integrate out, you can see that this will generate a log term in this free energy. So it will not be simply this, because the overdamping approximation has a role in this. So I've sort of tried to write it down. It's a subtle point. People who work with this sort of thing might be interested that the two continuum field theory descriptions are not simply you integrate out from the corresponding Boltzmann factor the G field. You also involve some assumption on the microscopic dynamics, and then you get the description only in terms of rho, or you get the description in terms of rho and G. Another thing is one can get this kind of description also from completely equilibrium consideration. Suppose I do not do any dynamic, I just take the some kind of force bearing function and then define the force grain function. So this is like over a shell, I average over the shell. So you can think of this as like delta function. And this is from a very old paper of Langer and Jim Langer and Kripke. And they were doing this sort of theories for condensation phenomena in those days. So you can write down again force grain field like this, where you sum over this. These are like definitions I've given you earlier. Only thing is there it was delta function. These people use some kind of force bearing function. Nevertheless, I can take this description, take the microscopic I can take the microscopic partition function e to the power beta h, take the trace of it, but with the delta function constant like this, that the average rho is come over this and this, you can calculate this. This is a very nice calculation in Langer and Kripke paper. And you can show again the F can be written as a sum of two terms which you get from the dynamics. That F is written as a sum of kinetic part and a interaction part, and then the relations are exactly. So that's conforming the dynamics with the static calculation. This sort of thing has been applied to MCT. You can write down the correlation function in a form with a renormalized diffusion constant, and the diffusion constant goes to 0 as you go to the glass transition. By glass transition, I mean the mode coupling transition. I'll not go into that here. Let me skip that. Let me just tell you a little bit on extension of this approach to self-propelled particle or active particles. So there, the equation that was assumed generally is of this form by Toner. This is from Toner and 2 paper. So this is their continuity equation in terms of the V field. Remember, this is what I am calling G, and this is in terms of the V field, the current equation. The pressure is written like this. So I can take again the same kind of Brownian dynamics equation and coarsen it. Only new thing I did is I generalize the frictional term in terms of momentum dependent frictional coefficient. A little bit like your approximation in the density equation for nonlinear diffusion equation. But so if I generalize this in this form, it's possible to write again the same sort of thing that you can write the density equation and the momentum equation like Fokker-Planck dynamics, average it over the coarse-grained it by averaging over non-equilibrium ensembles. And in this case, non-equilibrium ensemble, I mean not really a strictly Hamiltonian system, but I can think of some average density, average velocity of the particles in terms of that. And then you can obtain these sort of equations for the momentum density, which after certain steps reduces to this sort of, first of all, these are approximations. Let me first describe it. So I assume a general form for the kernel, the P-dependent part, which has a diagonal part and then an off-diagonal part. And then I assume that the momentum density on the average reaches some value delta naught. This is what is the temperature, but if the system is not thermal, then you can think of this average value of the density, momentum average. The diagonal part, I can assume a simplest form in terms of momentum variable like this, and then the off diagonal parts and all that. So if I put all this form, then there is a static part or symmetric part in this which can be written in this form, and then there's an antisymmetric part. The dissipative part can be written in terms of gradient expansions, typical things done in hydrodynamics, and then we can obtain the coarse-grained equation, similar sort of coarse-grained equation I showed you for the passive system into a form like this, which is the Toner 2 equation. This equation is almost same. There are certain nonlinear terms which are a little different as uh, this Toner 2 equation. Those of if you are interested more in this, look in the 2018 medical review paper. That this equation you can obtain.
But this is starting from which dynamics?
Huh?
Starting from which dynamics? Microscopic?
Microscopic dynamics, same as, so this is what I'm calling active Brownian equation, that I took this equation. So you can see the dissipative term is more general. Okay. So in the earlier case, this would be just a constant. Now it's a matrix form with a momentum dependence, and I put the momentum dependence to get it in this form. So by bringing in momentum dependence in the equation, you can obtain the active matter or the Toner 2 equation. This is in 2018.
So, how do you generate that middle form, alpha naught minus beta?
This came from this is what you are asking is technical. This came from when I take this thing, right? This is the dissipative term. Then I assume it to have a diagonal part and an off diagonal part. It's the diagonal part that gives rise to this. Now, you might say that how do I know what is its value? That the theory does not. That you have to do in specific case and all that. But I'm trying to show that if I start from the sequence, then I can get it in this form. Now, obtaining these sort of equations from microscopic has also been done by these people, Bartin, Ramasamy, Srodha, and others. What they do, they take the other way of doing hydrodynamics from those equations. That is the Boltzmann equation approach. You take the Boltzmann equation, you average it, and then do it. How much time do I have? 5 minutes. So that's another way of doing it, and it has similarities, but this is not related to any dimensional issues, whereas this is done in 2D. So what they showed here, that it's the friction between the two surfaces in this active system that plays a key role in having the Galilean invariance and all that affected. What we could show, and this is was still not published, that if I take this sort of approach that we are doing, and we can calculate entropy production and all that, we can show that from positive entropy production, that only in those cases where there is positive entropy production, that means the system is dissipative, then you have the frictional part that brings to this effect of Galilean invariance breaking. So, first of all, this is what Punavata was asking, that where does this thing come? As I said, that this frictional term you assume is a general form like this, and then the diagonal part gives rise to this. This term, as you can see, also breaks Galilean invariance. It doesn't, it remains invariant under Galilean transformation. But what Toner and to actually appeal Galilean invariance breaking is putting a factor of lambda here. If lambda is 1, then you are back to usual hydrodynamics, and this part 0, of course. But if lambda is 1, then you are back to the usual hydrodynamics with Galilean invariance. If lambda is not equal to 1, then you are away from that. So one can try to see how this lambda can come. So what we did is we modified these sort of invariance or the relation between moving and co-moving frames, between the lab and the co-moving frame, with some introduction of some local parameter Fi, and showed that if all the Fi's are constant, then you get the Galilean invariance. If the Fi varies from particle to particle, then it is Galilean invariance is broken. And what one can show that it's the variance or the moments of these Fi's that relates to the lambda. So if all the Fi's are constant, then these are constant. So it just they're same actually. So they drop out, and then you get lambda as 1. If they are not, then their Galilean invariance is broken. I have only 2 minutes, so just to mention this work we are doing now. If you bring in rotational degrees of freedom in these sort of systems, so instead of having only the Brownian dynamics I showed you, which was like this, that you have dr alpha dt, the position variable times this, you bring in some rotational degrees of freedom. So you have a torque, okay? You have angular momentum, and then local director variables. To painful calculation, you can actually show using the same sort of thing that you can write down similar sort of equation as Dean's equation, at locally average it, and then similar equations that we have showed for the Dean-Kawasaki equation. You can get things. Only thing is that D now gets over a wider tensor, and you have the wider tensor of the of the dissipative tensor, that you D, I, J, and so on. Your equations now at the Fokker-Planck level will also involve equation for the angular momentum density, not only the linear momentum density. So all this works out nicely, though quite involved calculation. You can relate the free energies in the two cases. Let me summarize it. So first, I wanted to I sort of discussed the microscopic balance equations, told you about Brownian and the Fokker-Planck dynamics. Then just try to give some impression of the coarse graining of microscopic equations by averaging over local equilibrium ensembles. Then this part I really could not cover. That is the deterministic dynamic DFT equation. This is not my word, but I thought that I'll say, but ran out of time. That is, so far I have already only told you about density equations, which are fluctuating equations. That means you have noise in the equation. There is another kind of equation for density that is used by people like Hartmut Loewen, Archer, Marconi, all these European groups, which is a deterministic set of equations for the dynamic, for the density functional system, which are also called dynamic DFT. But there, what they do is they average over the noise and then consider that density. So you get an equation which is very similar to the Dean equation, but you do not have the noise. This I could not discuss. There are very nice paper in 2009, I think, in JCP by Archer and Rocher. You can see how those sort of things are done. Try to discuss quickly a little bit of the application for self-propelled particles. Matter, Toner 2 equation. Breaking of the Galilean invariance, again, I was very short, but try to at least indicate how it comes. Then mention fluids with rotational degrees of freedom. That is, if you extend the set of slow modes, where not only translational degrees of freedom is there, rotational degrees of freedom also included, then you can write down similar equations. Now, just to finish, I've only told you about the equations, how the equations are written. That itself is a problem here. The focus is on that. But there has to be a reason for this. One of the main reasons of this is to, first of all, look at the nonlinear effects that come. These equations often become very nonlinear. So, how you treat those equations with nonlinear equations, or you want to calculate correlations of this kind of continuum field. So, you have correlation functions. So, to calculate this, you average over the noise. There are very efficient and useful methods using field theoretic techniques, often borrowed from quantum field theory, that you can write diagrammatic contributions for order by order for this kind of nonlinearity and calculate corrections, transport coefficients, which gives rise to again theories like glass transition, mode coupling theory, replica theories. Those sort of things we do, but I have not tried to discuss that. All I have tried to tell you is that under different conditions, how this kind of dynamical equations for continuum fields are. Thank you.
Thanks, Professor Das, for this nice and elaborative talk. So you can take a few questions.
When you are calculating the local average, then you are defining the probability values. So there that involves the corresponding thermodynamic intensive thermodynamic forces.
Yeah.
How do you actually practice and calculate in such models?
So what do you mean by actually calculating? What is that is done is you have a situation where the system is not in equilibrium, right? You take the corresponding equilibrium and borrow that idea. Suppose you have a system in which you do not have is absolute strict inequality. So density is constant everywhere, right? So you have chemical potential which is a function of only the whole system, just one chemical potential, one temperature, one velocity if there's a requirement. So these are all constants. Now, think of as if there are small areas in which locally the field is equilibrium. Then you generalize this, write down local equilibrium functions where instead of having constant temperature, you bring in a temperature dependent. That's all that is done. And the rest is that you assume that those functions that you introduce are not very strict, sharply varying, so that you can reduce your theory up to a first order invariant. When you take the first order invariant, you get this sort of. You take second order, you get Barber. It's all constructed on the basis of what is known. So from what is known, you go one step further. In specific cases, when you consider specific cases, there you have to know that how is it proportional to the density or gradient of density, gradient of temperature. So there are all these factors of transport coefficients. This sort of theory doesn't actually calculate. What it calculates is if in addition to that there are couplings of nonlinear fields, then how does those nonlinearities, which are in general terms almost couplings?
Any more question? So, is this thing that you said has got any semblance of, let's say, projection operator techniques used to get the degrees of freedom and to get an effective distribution? Is there anything to do with that?
Yeah, it's the same. It's the same. Only thing is that's called the Moore's one zip projection. But now, you see, when you do that, that's an abstract projection operator. You take a projection and then you project the system to two parts. One is the projected part and the reverse part. Here you can see you are doing similar sort of thing. You are projecting in the space of slow variables. Now, this is where Morris one scheme when you write, you just arbitrarily define a. You do not say why it is slower. You define it, you define the rest of it. And then you can write down the equations just from their identity that P plus Q is equal to 1. That is, the projected and the transverse part is equal to 1. You can write down formal equations for this sort of thing. But if you go into it, there are very nice papers of Guanzi that you really want to close them down to closed equations like this, then you have to do approximations of the memory. And that is similar to this. Only thing I would say in this case is more controlled. You have a controlled way of doing the approximation. You can go order by order in group theory. There you say, well, I just replace the 4-point function by 2-point function. But it's the same. But I think that this has a better control over the theory, that how the different nonlinearities will affect and all that. And I can go on talking about that, but there are many examples of that already.
Thanks, Professor. That's one more.
Is there any online question?
No, no, there is no online question. I've checked.
No, maybe you ask.
Yeah, from online, any question is there?
I have one question. May I ask?
Yeah, sure. Please go on.
Yeah, so I had actually two questions. So one was whether in the fluctuating hydrodynamics equation that you're getting, the noise remains multiplicative, or is it just the noise strength is only a function of the non-fluctuating average density? Let's say even in the Dean's equation problem.
Yeah, the two things you said, when you say Dean's equation, you're talking about a specific equation, right? So in that case, yes, the noise remains multiplicative. The noise is multiplicative. Originally in the microscopic equation, yeah, you can call it noise is multiplicative. So if it is Dean's equation, yes, noise is multiplicative. By Dean's equation, I mean the equation only in terms of the density. But if you do the equation in terms of density and momentum density both, you can hear me, I hope.
Yeah.
If you do this in terms of density and momentum density both, then you do not have multiplicative noise. You have only simple noise. But there is a different thing there. There, in those equations, you get nonlinearities which are like 1 over rho type, whereas in this case you do not get. So there is a difference and similarity in the two cases. In one case, you get what for low nonlinearities, but do not get multiplicative noise. That is the fluctuating hydrodynamics case, which I use the term for the case in which you consider rho and g both. But if you consider only the rho field, which is the Dean's case, then you get multiplicative noise in the coarse-grained equation.
Okay. I have one more question, which is related to some comment that you made about using renormalization group. So my question was, so for example, if you take the Dean's equation, which is just the microscopic density equation, you can define a microscopic Martin-Cgros Hamiltonian, right? And is there any work which would do some kind of RG scheme and show how does this microscopic Hamiltonian would flow to some effective Hamiltonian at the coarse grain limit?
Well, the answer to the question is, first of all, I think I said renormalization. I did not say renormalization group. Maybe online you didn't get it. I did not use the term renormalization group. I said renormalization. So what I mean there is that if you want to renormalize the transport coefficient, I mean, it seems you know those things. So I'm going a little technical, that if you renormalize the transport coefficients, that you can do using this kind of models. Okay, like let's say the mode coupling terms, you have the first order term, second order term, and so on. Renormalization group is a different thing. There, of course, yes, what you are saying. This kind of calculation are the most basic of it is the Foster-Nelson-Stephen that you most probably know, which was done in the turbulence case. And then I think Raman Goldstein and they also have done this sort of models with renormalization group. In the glass context, I'm not sure I have seen that application of renormalization group. I'm not talking about renormalization. Renormalization we are doing all the time, but not renormalization group.
Okay.
Renormalization group, that I can say, I would say the best reference is Foster-Nelson scheme.
Okay, Foster-Nelson scheme. Okay.
By this I mean the Foster-Nelson Stephen Physical Review A, I think in the 70s, which is just Foster-Nelson Stephen's name will do, I think.
Okay. Okay. Thank you very much.
Okay, thank you everyone for joining online and offline in this talk. And I think tea is outside. You can join there.